Okay, sorry about that. I was saying that if you have any questions for the participants that are online, feel free to use the chat function and we are monitoring it. And at the end, we will be able to share the questions with Professor Thivierge. But for now, it is truly my honor to be able to introduce you to my colleague, Professor Jean-Philippe Thivierge, who received his PhD from McGill University in 2006. He then worked as a postdoctoral fellow at Indiana University before moving to the University of Ottawa, where he is now a full professor at the School of Psychology and also the Associate Vice Dean of Undergraduate Studies at the Faculty of Social Sciences. His research focuses both on experimental and computational approaches to study neural activity, plasticity, and repair in brain circuits. Today, he has graciously accepted to share his personal experience through a presentation titled Healing Beyond Survival, Bridging My Cancer Experience with Research for Change. Thank you, Jean-Philippe. It's truly an honor to have you here, and we are very excited to hear your presentation. Please join me in welcoming Professor Thivierge.
So, this work? Okay, good, good. Well, I want to say thank you to Nafisa and members of the Life Institute for inviting me to give this talk today, which will be a pretty different talk than the typical scientific talks I'm used to giving at conferences, because you know, this kind of started a while ago when I reached out to the Life Institute and Nafisa and said, hey, you know, like I'd like to see if I can present sort of something in between my life experiences, as you're going to hear about in a few minutes, and how that's kind of contributed to research. So there's going to be a bit of a mix of sort of more personal and more scientific-based approaches. And I'm going to try to be careful to highlight what reflects my opinion and what has, you know, scientific basis by adding proper references whenever I could find them. Okay. Oh, and I did bring a few props as well that I will reveal when the time comes. Okay. Let me see. There we go. Okay. So this is a brief outline of what I'm going to be talking about today. So an overview of my journey so far. I'm going to talk about some kind of advice regarding cancer survivorship. So those of you that have been affected by cancer experience or have a close one that was affected, some of my personal experiences, and like I said, scientific literature as I can find it. And third of all, I'm going to bridge into my own research into brain resilience. Okay, so this is a very brief outline of my journey. Did my undergraduate degree at U Ottawa here in the 1990s. PhD from McGill, first postdoc at University of Montreal, and then I moved to Indiana University, then came back to Ottawa, worked at the National Research Council for a few years, got recruited here at U Ottawa, and then finally, you know, here I am in the Faculty of Social Sciences, still a professor and acting as Associate Vice Dean of Graduate Studies. So it's been kind of an interesting kind of full circle loop here. But one of the things that's made my journey very different from a lot of you out there is that in summer 2011, literally 4 days after I learned that I was now going to be a professor at university here, you know, I'd worked my whole life. This was my dream job. And I had all my books packed in boxes, ready to be unpacked and start enjoying my time here. I learned that I was diagnosed with stage 2 seminoma, stage 2B seminoma with metastasized cancer. And so from there on, you know, I just basically abandoned everything in my office and had to look after my health for several months after that. And then from 2011 to 2019, I underwent a whole bunch of different procedures, and I battled that for a good 8 years before I was deemed free of cancer in 2019. So it was definitely a long journey, and I want to kind of share my experiences with that, and maybe a few nuggets of wisdom along the way. And there really are three things that I want to talk about and emphasize today that kind of, I feel, have helped me and may help other survivors in that same position. And one of them is the idea of building a community of survivors, so being able to associate with other people that have had a similar experience, relearning the mind-body connection. So cancer really creates that disconnect between your own mind and your ability to trust your body. And third is my way of giving back, which I'm going to describe very briefly, a project called the Second Skin Project. So the first thing I want to talk about is this idea of community building. I've been involved with an organization called YAC, Young Adult Cancer Canada, and it's really like they're affiliated with Cancer Canada, but they're a branch specifically for young adults diagnosed with cancer. And young adults face particular challenges when you're diagnosed with cancer in your 20s and 30s, because it's a time of your life where you're thinking about relationships, maybe about starting a family and a career. And so there's unique challenges that are not necessarily the same as when you're diagnosed with cancer as an older adult. And so the group is really focused on organizing activities, social connections, support, where you can really kind of share with others what you've been through and what they've been through. There's also events and conferences, seminars, awareness also. So we participate in the Terry Fox Run every year, and fundraising as well. So all these activities make it a really kind of fun and dynamic group to be a part of. And here's a few pictures of that. This, the one on the left here was Relay for Life. It's fundraising and awareness activity. And that's where I met my wife now, Jennifer. We've been married for 11 years this year. And so it was definitely beneficial for me to join that. So in terms of benefits of community support, so this is more like the science-backed evidence why this is so important. And one of them is reduction in psychological distress. So obviously faced with a diagnosis of cancer and planning for treatment and recovery, you're faced with tremendous psychological distress. And so we know that finding a peer support group of people that have been through a similar experience can really help alleviate some of that distress. The second point is enhanced coping and adaptation strategies. So for example, recognizing when you're having negative thoughts. So, negative thoughts regarding your cancer outcome, et cetera, can be very overwhelming. And so being able to share that, recognize it, engaging in meaningful and enjoyable activities. So just being able to say, okay, I'm going to put a pause on this whole cancer thing for a while, and I'm just going to go out and have a good time. And we've had tons of, we had board game nights, bowling, et cetera, tobogganing, relaxation techniques. So being able to learn to just kind of breathe and focus on something else. Problem-solving skills. So we're often faced with challenges when talking to family members and friends about the diagnosis and treatment, but also talking to healthcare providers. And it's very important that when you go and meet with healthcare providers that you are well prepared, you have questions in advance, and you can anticipate certain answers, and you can navigate through that. So patient advocacy is very, very important, and it can really promote a positive outcome. Dealing with fear of recurrence as well. So even though you're done with treatment doesn't mean that the anxiety and distress goes away immediately. It's something that can linger for years afterwards. Every time that you have another test coming up, another appointment, you fear that your life could go upside down again. And so dealing with that and finding other individuals that have that same experience can help you. And communication skills, as I mentioned, very important to know how to seek support, how to talk to people around you, because one of the fears that a lot of cancer survivors have is they don't want to seek support from their peers because they don't want to overwhelm them. And so knowing how to navigate that is very important. The second point I want to bring up is this ability to relearn the mind-body connection. And it really feels like when you've gone through that sort of experience, and whether it's cancer or another health-related issue, you kind of feel like you can't trust your body anymore. Like, what's going to happen next? What's my body going to do next that's going to kind of like betray me and betray that trust? You know, you're like, hey, we've always got along well. You know, like we used to go biking and we used to go running, and now there's a lot of physical limitations that I didn't expect would be coming up. And so learning to trust one's body again and adjusting to the loss of some physical capabilities. So maybe there are certain activities that you could do before that you can't do now, and learning to adjust to that is very important. And managing some of the side effects associated with cancer and treatment, whether it's pain, fatigue, memory impairments. So cognitive memory impairments, which I'll talk about later, could be related to the treatment, but they could also be just related to the anxiety around the treatment and just feeling overwhelmed with everything that's happening. Changes in sexual function, depression, anxiety, fear of recurrence, and planning a return to work, because I went on medical leave because of cancer, but I had to plan to return to work 3 months later. And I remember clearly going to human resources and saying, hey, I'm going to need a medical leave from my teaching or professor duties. And I had all my paperwork. And the lady at HR, she looks at that and she goes, "Ooh," she goes, "there's no way you're going to be back in 3 months." And I said, "Yeah, I'll be back in 3 months." And I was back in 3 months, and it was difficult at first, but I took it as a challenge, what she said. Okay, and one of the things that's really helped me personally through this journey is being able to engage in strength training. And I've been a huge fan of powerlifting for about 15 years now, and I continue doing powerlifting throughout cancer treatment and recovery. And I did find some papers backing that up, that strength training during and after cancer treatment can be beneficial. It's very, very difficult, however, to find individual guidelines for a person who's going through treatment or after treatment to say, okay, what should I do? What can I do? What is medically realistic and what is safe for me to do? It's very, very hard to find those guidelines and to find doctors or medical professionals or physical therapists that know exactly how to navigate that. Rebuilding muscle strength is very important following cancer treatment and bone density, because there's a loss associated with your diet during cancer treatment, the fact that you're nauseous, the fact that you're stressed out. And so I find that could be very beneficial. It can have obviously a very positive impact on mental health. So lifting weights can empower you as an individual, but can also allow you to connect with a group of people who have similar interests, and that's a support system in its own. Can increase your levels of energy. And my own personal recommendation is really this last point here, is being able to go at your own pace. So I started weight training, and I don't recommend necessarily doing this. Again, individual approaches are important, but I started weight training again 4 days after surgery. And the doctor, I didn't tell the doctor at the time, they would have cringed. But basically, I walked into the gym asking, what can I do now? So basically, I ended up having abdominal surgery. And so I said, well, maybe I can train my arms. And so I went in and I lifted 5 pounds. And it was a humbling experience, because before surgery, I was lifting, say 200 pounds. And then, coming in, and I just said, well, I'll just lift the bar or 5 pounds or whatever. So what can I do right now? And what feels okay for me to do without any pain or discomfort? Using light loads and using limited range of motion if necessary. You don't have to do the full Olympic lifts. You just do whatever it is you can do and respect your physical limitations. Simple exercises, so stick to the basics, don't go online and look at all the varieties of things, stick to the simple things. Short workouts, so if you can only handle 10, 15 minutes, that's fine. It's whatever you can do. Focus on a gradual progression, so maybe from 1 week to the next, if you're feeling like your body is responding well, you can say, well, maybe I'll add 5 pounds, or maybe I'll do 1 extra set than I did last week, so you feel like you're progressing. And consistency, so I highly recommend that whatever it is you want to do, even if it's simple, that you do it consistently from week to week. And that's essentially what I've done. And I guess my last point of advice on this is track your progress. And it's very empowering to do that. And I'm a geek when it comes to numbers. I love numbers. I work with numbers. And as you'll see later, I work in AI. And so I've been tracking my progress in weightlifting consistently every day since 2009. So I have an awesome data set of one person, an N of one, of every single lift that I've done. So 2009 was before my cancer diagnosis, and 2024 now is obviously today. So I have all the data. I'm sure nobody is ever going to be interested in it from a scientific point of view because it's an N of one, but the data is all there. And the other benefit that I found for myself is taking regular videos of the lifts, because now with advanced software, you can use techniques like AI to track things like the bar path when you're lifting the weight, and that allows you to perfect your technique. And technique in weightlifting is extremely important. Like they say that strength is really a skill, and so it's something that you can develop over years and years and years. And being able to use software like the one you see here, where the camera allows you to track the path of the bar, is something that makes a huge, huge difference. Okay, and with all that said, so one of the goals that I had and finally reached in 2020 was winning the national championship gold medal. And so that's one of the props that I brought today. So I thought I'd show you guys. So 5 years ago, literally 2 weeks before everything shut down for the pandemic, I came back with the gold medal, and then my gym shut down, so I wasn't able to even show this to anyone. It's like on my own at home and enjoying that, so that's fine. But yeah, so that was one of my goals, and my next goal now in 3 years is to actually beat the national record in the bench press. So we'll see how that goes. Okay. The other aspect of the mind-body connection that's really helped me personally is ice dipping. And some of you may have heard this before. Now, I'm going to say first thing is you should all consult with a physician before doing this, before attempting that. However, I want to emphasize again that there is a lack of individual guidelines to do this. So it's not like you go to a physician, he can systematically look at your medical history and say, yes, I recommend it, no, I don't, for how long, for how much, etc. So those individual guidelines don't really exist. There's kind of a bit of a vacuum for that. And I want to emphasize also that I think that the potential health benefits of ice dipping recently have been largely overplayed. And I want to emphasize the studies on this that have shown positive effects. So potential benefit for muscle soreness, I would say, is largely individual or largely anecdotal even. So there's evidence that suggests that there is really not much of an effect in terms of muscle soreness or recovery from workouts. In terms of positive impact on immunity, some effect, limited again. And decreasing the stress and anxiety, there's a recent paper that suggests that there could be some effect. But again, I would say that while you're in the water, it may not exactly be true. And some of the other benefits, such as blood pressure, heart rate, or heart function, have no documented effects there. So some of the things that have been really, really overplayed with this recently, and so I want to emphasize that this is personal choice, but it's something that I've enjoyed tremendously. How to get started? Those of you who are interested in trying it out or curious about trying it out, I recommend starting with cold showers at home, 10 seconds, and then increasing gradually. It's not as much fun in winter as it sounds. There's also a growing community of ice dippers. We have a group on Facebook called Coldplay Ottawa with 803 members and growing every year. And what I really like to emphasize for people who are getting into this is this idea of year-round dipping. So essentially, I do ice dipping in the lake or in the Ottawa River every week, and I do this on a yearly basis. So in the summertime, it's enjoyable. I bring the kids, we have a picnic, it's fun. And then I just keep doing it year round. So you kind of learn to follow the flow of the seasons. And when the weather gets colder, well, you just keep enjoying it for sometimes shorter amounts of time. And with that said, a couple of quick additional tips on that. One is this idea of mindfulness, which connects with ice dipping in the following way. I find that it's very important that when you're entering the ice water, that you create this mental space between your thoughts, emotions, sensations, and your reactions to them. Because when you enter the cold water, your immediate reaction is almost like panic. You gasp and you take a deep breath and you go, because it's such a shock to the body. But mindfulness helps you kind of create a gap in between what's going on in your body and what is your actual reaction to that. So you can start by taking long, deep breaths. So when somebody gets in the water, I've coached people who are ice dippers for the first time, and they get in the water, and I say, follow your breath, follow my hand with your breath. So I put my hand closer to their face, and I take long extensions like that, 5 seconds in, 5 seconds out, and people learn to take very long, deep breaths. And after they get past the first 30 seconds, they go, wow, this is actually really fun, for the most part. So mindfulness has been shown to reduce cold-induced pain perception. So being able to refocus the mind and create that split or that distance between what your body feels and what your mind interprets helps you reduce that perception of pain. And the other thing is obviously deep breathing is extremely important. So that's why you have these people like Wim Hof, et cetera, who teach breathing methods. Because if you get in the cold water and you gasp like that, you're going to have an awful time. So learning to breathe is very nice. And I find that for me, when I get in the cold, all the thoughts that have been going on in my head of like the little stress, like, oh, I need to pick up groceries and I need to finish this paper and I need to do that. All that noise just goes away completely for 2-3 minutes. So it's really wonderful to have that. And in January of 2023, we actually broke our Guinness World Record in Kingston, where we got more than 50 people laughing in the ice for more than 30 seconds. And I want to emphasize that because what happened at that event was that the Guinness World Record people were there filming using drones. So they had aerial drones to film how many people were in the water simultaneously. And so because of technical issues and all kinds of other things going on, we ended up staying in the cold water in Kingston for more than 6 months. So it was brutal. It was brutal. And then I got out, and my wife was there helping me, and I had like a thermal bathrobe, but the sleeves were inside out, and I totally panicked.
See you on the picture though?
I don't think I'm in the picture there. No, I did. I was able to find myself in another picture, but this was the official picture. Yeah. Okay. Very briefly, the third thing I want to talk about with respect to cancer survivorship before we get into research is this idea of giving back. So I wanted to kind of find a way to sort of take my experience and give back to the community of cancer survivors. And so a few years ago, and this is still sort of a project that's in its infancy and we're still developing it, is something that I call the Second Skin Project. So I'll explain what this is. So tattoos are part of radiation preparation. So when you are scheduled to do radiation therapy for cancer, they have to tattoo your skin to know exactly where to position the radiation beams. So it's very, very precise. They have to target organs within your body, and it's extremely important that they know exactly where the laser needs to go. And so they actually put permanent tattoos on your skin. Now, those are not the same tattoos that you'll get in your local tattoo shop, because those are done with a pick and poke. So they're done by hand, and they're done very deeply, and the marks are like, they look off, okay? And so some people view them more as like, badges of honor that they've gone through it. But for a lot of people, those are permanent scars and mark, and they're just a painful reminder of their diagnosis and treatment experience. And it's truly the case for a lot of patients, breast cancer patients, and many types of cancer that have gone through radiation. And so I teamed up with YAC, and we came up with this idea that we wanted to help people that have gone through cancer treatment and have these cancer scars and tattoos to be able to cover them up with better looking tattoos, nice tattoos that they actually chose and kind of reflect who they are a lot more. And so what this really is an opportunity to match cancer survivors with pro bono tattoo artists, whether it's in Ottawa or outside the region here, who are willing to bring in, cancer survivors and tattoo whatever they want. So this is just an example here We also do fundraising for people who already have a tattoo artist, but they're just looking for funds to be able to cover up their tattoos, and raising awareness of cancer scars and tattoo management as part of the healing process for a lot of people who choose to do this and to choose to cover them up with something much more meaningful to them and much prettier than having a whole bunch of cancer scars, okay? And this really is nice for a lot of people because you kind of feel like you kind of graduate from being just a cancer patient to being really a true cancer survivor, you know, with something really cool on your skin that you can show off. So this is really a project that's still very much in its infancy, but I would really like, that's the reason I'm talking about it, I really like to try to grow it over time. Okay, now we're going to move on to more the research component of the talk in the time that I have left. And really, there's two questions that are sort of interesting to me in terms of brain mechanisms and kind of bridging into my own experience. It's, first of all, how to protect neural circuits from damage due to radiation therapy. So patients that are specifically undergoing radiation for brain tumors experience cognitive impairments, but also damage to healthy tissue within the brain that are usually surrounding the sites of the tumors. And second is, if there is some damage to cognitive or neural function, how to restore it following treatment. So those are kind of the big questions that we're trying to address. And so really the brain is this large network of interconnected neurons. It's extremely complex. And I remember I gave an interview once for a newspaper, and the interview went really well, and we talked about research and everything was great. And then when the news reporter left my office, we were kind of just joking in the hallway. And I said, well, you know, I said, the brain is really this complex thing. I said, it's kind of like a bowl of spaghetti. And that's what ended up being an article. So just be careful what you tell reporters in interviews. Okay, so what happens to brain networks following radiation therapy? Neuronal necrosis. So radiation itself can induce neuronal death for various reasons. Dysfunction, so higher or lower levels of activity. And so brain regions like to have a targeted level of activity. So resting state activity is typically around 5 hertz. And so higher levels of activity can be induced by radiation. I'll show examples of that later. And cognitive effects of that on memory, executive function. So there's really two strategies that we've come up with to try to see how we could limit or prevent damage. Number one is pharmacological intervention. So for example, preconditioning. And the second one is lifestyle recommendations. And that really ties into sort of benchside to bedside practices where we try to extract something meaningful from the science to try to help sort of guidelines for patients in the clinic. But that's really sort of more of a longer term goal.
Est-ce que tu parles de are you talking about radiation, any kind of radiation, or just for brain cancer?
So the research I'm going to show is specifically for brain tissue, but there are situations where, for various reasons, radiation damage can cross the blood-brain barrier. And sometimes it's radiation damage itself, and sometimes it's the drugs that are used to treat aspects around that. So I'll talk about that. See. Okay, so in my lab, the tools that we have basically are, and I brought the other prop here to show you guys, these are called multi-electrode arrays. I'm sorry for the people online who will not get to see this in person, but I'll pass this around. So this multi-electrode array is basically a computer chip that interfaces with brain cells. So as you'll see, there's a well in the middle, and in the well, there's liquid called artificial cerebral spinal fluid, and that keeps the neurons healthy and happy. And the neurons make contact with the chip that's in the middle of this. And if you were to zoom in, well, you can't see it by eye, but the chip is basically like a hairbrush. So it has tiny little pins sticking out, and neurons are sitting on that. And it's a little bit like microphones. So it's a little bit like if you have a room full of people and you drop microphones in that room and you can record the conversations going on. Now, the challenge with that, of course, is that you have about 100 to 200,000 neurons, and you've only got about 4,000 microphones. So you're trying to extract as many conversations as you can, given that limited capacity. However, 4,000 channels, or 4,096 channels, is still a lot. You can record simultaneously from these channels at single cell resolution for 20,000 points per second. So 20 kilohertz is 20,000 points a second. So roughly speaking, in about a 5-minute recording, you end up with something around the order of about 5 terabytes of data. So my students, and Camille is in the room here, know that on a day-to-day basis, what we really do in our lab is data analysis. We use custom scripts, et cetera, to try to extract meaningful patterns from this large data set. And that is, in fact, what we end up looking like some of the time. Okay, and over the years, I've published many, many papers on that, and I'm happy to share references later. But just to say that this is kind of what my background is in recording neural activity from large populations of neurons. And here's a little video. This is an example of recordings from hippocampal cells. So these are cells that are located deep within the brain and play an important role in learning and memory. And you're going to see patterns of activity propagating in these. So there you go. So there's a burst of activity there, and it really follows the structure of hippocampus here. The resolution here is beautiful, and it's much better than what you would get with, let's say, an EEG type thing. So this is like, you can think of this as like a micro EEG, where each channel kind of covers 50 microns, about 50 microns in diameter, and we have about 1.2 centimeters on the chip. So each pixel here is one of these 4,096 pixels. So the data resolution is huge. Okay, now how does this tie in with radiation? So we had this study that we started back in 2019 with my now graduated PhD student, Megan Boucher-Routier. And unfortunately, the study was interrupted temporarily due to the pandemic, where we weren't actually allowed into the radiation center for health reasons, but we did pick it up later on. And the idea was basically that we can take healthy brain tissue and expose it to the same types of radiation therapy that human patients are being exposed to in the clinic. So literally, what Megan did is she went to the radiation center at the Ottawa Hospital after clinical hours. So she usually would start working around 4 p.m. and perform these recordings often until midnight or even later. And we calibrated the machine. So this is the CyberKnife at the Ottawa Hospital, with the help of Dr. Vimal Jner, who's a radiation oncologist there. And we calibrated the machine so that the amount of radiation received by our cells would match exactly what patients are receiving during treatment. So there's a lot involved in that procedure, but I kind of just wanted to give you the highlights of that. And what we found was really interesting. This is a control slice where we examine conversations between pairs of neurons in cortex. And every time there's a line here, what this means is that there's a significant correlation between the activity of 2 different cells in this culture. So it means that there's a conversation going on. Now, this is a happy, healthy conversation. This is lots of noise. So this is 20 gray radiation, 50 gray radiation, and 100 gray radiation. Now, the doses of radiation can vary based on patient sort of treatment plan, et cetera, but up to 100 gray, this will be qualified as like very high dose radiation. So what we see is that there's an increase, not in the quality of conversations per se, but really in the quantity of noisy conversations going on. So the analogy I like to give, which is admittedly not the best one, but it's a little bit like a very dysfunctional married couple who talk more but communicate less. Okay? So that's what's going on in these preparations. And I can also emphasize that we compared these results with the type of connectivity that we see in epileptic slices. So the bar at the very far right is where it says EP. That's a slice that's been stimulated by a substance that generates epileptic seizures. And you can see there that the correlation is really, really high. So it's not that these radiation-induced patterns are caused by or causing seizures itself. It's more like the level of activity is increasing. And so you can think of these as kind of road maps, if you would, like this would be, a map of the city of Ottawa. And so what's really happening with radiation is it's causing a lot of congestion on these roads. So it's a little bit like causing road rage, okay? So what we would ideally like to do is to prevent this from happening, because we know, based on some of our past studies, that increased communication like that can actually put neurons on the brink of necrosis. So pathologically increasing activity to a very, very high degree can essentially cause neurons to die. And in fact, that is what we saw. So Megan used propylium iodine staining in these preparations, and she showed that you can label neurons that are basically the cell membrane potential is essentially just rupturing, and ionic material is spewing out of the cells. And it's really hard to see here because we have the blinds up. But if you have the blinds down, there's increased luminance as you increase the dose of radiation here. And that's what's shown quantitatively in the figure on the right-hand side, where we just look at the brightness or intensity of these images. And you see that there's a dose response where higher doses of radiation increase the PI staining, which is related to neuronal death. So ideally, what we'd like to do is to try to find the right balance between a dose of radiation that provides therapeutic effects and one that doesn't cause neuronal death. And that's where that tough balance really lies. So one of the key advantages of using microelectrode arrays like the one I showed you is that we can actually perfuse it with drugs, with pharmacology, either before, during, or after radiation treatment. And so one of the things we're starting to look at now, and this is work that's ongoing right now, so I don't have really a lot of really like finalized results, but I thought I'd share anyway. And one of the drugs we're playing with is serotonin drugs like Zofran or ondansetron. And why we chose these types of drugs is because literally all patients undergoing radiation therapy is on Zofran. So do you guys know what Zofran does? What does it do?
An anti-nausea drug?
Exactly. So it's anti-nausea. The effects of radiation are cumulative. So day one, you go in and they zap you and it lasts 2 minutes. And you go home and you're like, wow, that's it? No big deal, right? By day 14 or so the treatments are done every single day. So in my case, it was every single day except weekends for 35 days. By the second week, you're like leaning your head out the window and feeling very miserable. So the Zofran is a drug that helps manage nausea. But what we don't know is whether that drug has a potential, enhancing or, interaction effect with the radiation itself in terms of inducing neuronal dysfunction or even promoting neuronal death. So here's one very quick result that we generated by simply elevating serotonin levels in cortical preparations. And this is a control condition. Each little blip here is an action potential from a neuron. And you can see over time that in control conditions, there's chatter going on, which is perfectly normal. It's at about a 3 to 5 rate, 3 to 5 hertz, so 3 to 5 spikes per second rate, which is normal, happy, healthy neurons. On the right-hand side, when you elevate serotonin, you start to see elevated firing rates and increased synchronization as well. And so the concern with this result is that if there's any interaction between radiation, which elevates neuronal activity, and serotonin, which also elevates neuronal activity, there could be a case where you get sort of the double whammy effect by doing both at the same time. And so the hypothesis that we're working with now, and I don't have any more results to show on that, but it's that elevated serotonin levels increase spike rates. And so specifically serotonin receptors like 5-HT2A, HT3 and 5-HT4 are known to increase excitability. And so there could be a potential synergistic effect between serotonin and radiation causing more neuronal damage. And so we need more research to confirm this effect by combining serotonin with the radiation, as I showed you earlier, which is what Megan was doing. But I need more students on this. I don't currently have a student to do this. And so why this is important is because I think that this could really lead to changes in the guidelines provided to patients in the following way. So imagine, for example, that a current guideline, and this is just one example, but guidelines are patient-specific, but imagine a patient that is told, for example, you can take 8 milligrams of ondansetron 1 to 2 hours before the radiation treatment, followed by 8 milligrams every 8 hours as needed. And this is very, very typical. I think this is basically what I was doing. So you take 8 milligrams before, and you follow afterwards. And of course, like, you don't want to, like, I always tried to take the minimum amount that I could because there are side effects to ondansetron. But I find that if you wait too long, you get really nauseous and it's really bad. So you kind of have to balance it out. Now, example of possible revised guideline, if we find that there's this interaction between serotonin and radiation, could be, for example, to delay the administration until after the session, so 2 to 3 hours post-radiation, to avoid serotonin elevation during peak radiation exposure. So that could be possible, and I don't think that this would be hard to manage in terms of nausea symptoms, because I think that the nausea symptoms usually occur several hours post-radiation exposure anyway. So that would be fine. Or potentially combined with alternative anti-emetics. So for example, NK1 antagonists so for example, you could say, well, I'm going to give a lower dose of serotonin and compensate that with NK1 antagonists. So those are examples of guidelines if we find that the research does head in that direction, and that could be beneficial for patient outcomes. The other thing that I think would be interesting in terms of research would be to look at the effects of cannabis. And again, I need more students to be working on this, but cannabis is very, very interesting as a drug that could interact with radiation therapy because, number one, many patients, between 25 and 40%, we estimate, we don't know, use cannabis during cancer treatment for regulating mood, anxiety, regulating sleep, appetite and nausea, headaches, etc. Now, there's a lack of precise guidelines on the interaction between radiation treatment and cannabis use. Does it matter if you consume cannabis immediately before radiation treatment? We don't really know. There's a few studies that I found on potential neuroprotection of cannabis, but not necessarily related to radiation, and lack of specific studies examining the optimal timing of cannabis administration relative to radiation therapy sessions. So a little bit like what I showed with ondansetron earlier, where we could adjust and optimize the timing of the drug with respect to the radiation exposure. Now, there are a few papers that are starting to look at that, but it's definitely nothing conclusive. And this is a question that we can address by using a protocol very, very similar to what I showed you earlier, where we perform recordings using the microelectrode array. We can directly put cannabis, like a cannabis oil, directly in the artificial cerebrospinal fluid that is perfused in the cells, record neural activity, apply radiation, and then look at some outcomes. For example, do propylamidine staining for neuronal death, look at neuronal activity, synchronization, patterns of communication between neurons, etc. And from there, maybe we can extract some meaningful potential guidelines that could guide clinical practice. So we're not there yet, but I'm hoping that we will soon enough. By the way, an interesting little fact is that even though cannabis is now legalized in Canada and you can go to any store and purchase cannabis, you have to have an exemption from Health Canada to use cannabis in lab research. And I didn't know that, and the process can take apparently months. So we're looking to file that at some point, but it's something that kind of took me by surprise. Okay, and finally, looking ahead, so the next couple of minutes of the talk, I want to talk about some very exciting work that we're starting to look at in the lab here, which is in the use of generative AI. So you guys all know what generative AI is, right? So for example, prompting for images, like there are websites like Canva where you say, give me a portrait of an astronaut with a jetpack in space with flames, etc. And you're able to generate images from text. And so generative AI is now being used everywhere in research and is starting to even seep into neuroscience. And in the following way. So one of the things we would really like to do, and this is a little bit like a dream in the clouds, but would be to be able to record brain activity then use AI to kind of understand those patterns of activity, replicate healthy patterns of activity, and feed those back to the brain. So forming this kind of closed loop where you record brain activity, understand it using AI, and then go from AI back to the brain by stimulating the brain and recreating those healthy patterns of activity. And this is huge dream in the clouds, right? This is something that we would hopefully would be able to do one day. However, in the shorter term, we are able to do some of these things, at least as a proof of principle. And I'll show you one example here. So this is a paper that we published 2 years ago with my student Megan. And so we're able to record brain activity using the multi-electrode array. And then from there, we're able to use generative AI to replicate healthy patterns of activity. So we're able to use AI to create new patterns of healthy brain activity. And this is done using a generative AI system. And generative AI, those of you who don't know, the way it works is essentially two neural networks that compete against each other. So you have one that's the discriminator and one that is the generator. So the discriminator is a little bit like the art critic. So he goes, yes, that's a Picasso. No, that's not a Picasso. And then the generator is the one that generates copies of the art until essentially the two networks compete against each other. And then they kind of just at the end, they agree to disagree, right? So the generator becomes really, really good at generating almost perfect copies of the original. And the discriminator gets worse and worse at telling which is the true Picasso and which is not. That's why you can get these hyper realistic images. And I encourage you to, there's a website that's called, I think it's called thisisnotaperson.com, and it generates hyper realistic faces of people that don't actually exist. And there's even one called This Cat Does Not Exist, where it's hyper realistic pictures of cats. And it makes me so sad because the cats are adorable and they don't exist. So we can do this, and this is an example of propagating activity in a cortical slice. So this is a recording using the MEA, and we are able to use AI as a replica to generate very, very similar patterns of activity that look almost identical to these cortical waves. And of course, the next goal now, and that's why I wanted to talk about Camille's work, is then saying, are we eventually going to be able to use those synthetic images and feed them back to the brain? And Camille is analyzing data and building computational models where she's considering neurostimulation as a way to either suppress pathological brain activity or promote healthy brain activity. And we had a paper a few years ago in PLOS biology on that exact technique. Now, right now, Camille is using very, very simple patterns, like just simple waves or just noise or whatever. But what we would really like to do in the future is use hyper sophisticated patterns like ones generated by AI. And like I said, we are not there yet, but we're hoping one day we will. Right, Camille? Right. So in summary, sort of what I talked about today is the importance of finding your own personal roadmap to recovery. I've had my own roadmap, and it's been a very exciting journey, but it's not something you necessarily want to copy. You want to find your own. Continuing research into the effects of neuroactive substances on radiation. So I talked about the effects of serotonin and possibly cannabis. And looking towards the future, the use of generative AI for individualized treatment and recovery plans. So it'd be really nice to be able to understand brain activity using AI, but also plan for treatment and recovery using generative AI and restore healthy brain function. And that is essentially it. I just want to thank past and current grad students in the lab, a long list of volunteers, collaborators, and special thanks to a cancer survivor named Gavin Murphy, who was a private donor and helped fund some of the research presented today. Thank you.
We have time for questions.
Thanks, JP. That was, inspiring talk and amazing data. I'm So you won't be surprised to learn I'm curious about your neuronal recordings, and a couple of questions. One, I was very happy you showed a nice hippocampal recording. In your in the where you generated the spikes on those maps, do you see differences in response to radiation depending on the brain region? Like, do you get cortex versus hippocampus?
That's a really good question. So we've only done radiation on neocortical slices right now. We haven't looked at hippocampus, and I would be really curious because I know that there are regions within hippocampus, like the hilus, for example, that is hypersensitive to damage. And there are tumors there that we've seen in the clinic. So it'd be very nice, very important to target that. It's costly work to do though, because every time it's like, oh, I just want to add a brain region. Well, it's like you need X number of animals, slices, and you know, on a good day, on an average day, none of your recordings work. So yeah, but it's
Yeah, I was thinking mostly when you mentioned the hilus, I mean, the dentate is such a low sort of basal rate of activity versus say CA1 or CA3, which is much, much higher. So I'd just be really curious to see what the hyperactivity is in those regions.
Yeah.
That's great. I'll save my other questions.
Okay.
Give people a chance.
Okay.
Very naive question. When you talk about replicating normal patterns by AI to feed them back, why do you need to replicate them as opposed to just take what people generally produce?
Yeah, that's a really good question. Like, so you could, for example, just say, well, I'm going to just look at the activity of an average brain, and then I'm going to feed that into, but it turns out that patterns of activity are specific to individual brains in the sense that the connectivity pathway of your brain is different from mine, and we're both assuming healthy individuals, but our patterns of activity are vastly different. And there's computational studies that are coming out now on something called brain twins or brain clones. You had send me something like that. This is Victor Jersa. Yeah. So is it twins or clones, or I forget what term they use. Clones. They bring clones, and so what they do is they can basically take images of your brain, look at DTI, for example, and create a virtual brain, and then examine how patterns of activity would propagate in your brain. It has to be individual. And in fact, when we do this in computational simulations, we find that the best way to induce responses in these models is to feed them their own patterns of activity and not something external. So there's a lot of math behind mathematical reasons behind this, but the basic reason is that the brain is essentially acting like an attractor state. So it prefers to be in certain states of activity, and it knows which states those are. And by feeding it those states to itself, it's going to respond the best. If you feed it somebody else's states, it's like our brains internally don't speak the same language. Yeah, that's the non-scientific answer. Yes.
These brain slices, how fast do you have to act on it? Like,
yeah, so there's a few different ways. You can do acute slices that they will, if properly done and they recover properly, can last between 6 and 8 hours. So they're active, happy, and healthy for about 6 to 8 hours. Or something that we haven't done here, but the other option is cortical cultures. And in my past life at National Research Council, we used to keep cortical cultures happy and healthy for up to 90 days. And that's cool because then you can study longer term effects. So here we're really just looking at very, very short term effects of radiation, but obviously because radiation is cumulative and its effects can show up days, weeks later, it'd be really, really cool to do this in cultures. The problem is that I was going to say manpower. The student power required is greater for cortical cultures. You need somebody to tend to them almost on a daily basis. We've had, cases where they die and we don't know why, and they've had to be treated with serum, et cetera. So it's a lot more involved, and we just don't have the technical personnel to do that. So the other disadvantage with cultures is they don't keep the exact same anatomical connectivity as the intact brain. But then again, you could argue that slices are also cut off. So, I mean.
I have a personal question, which you don't have to answer, of course.
Yeah, sure.
But you started off by talking about very subjectively about your cancer experience. So when you look back, do you have, how can I say this, sort of I mean, it sounds to me like you're looking at the positive aspects of having gone through that experience, as opposed to having it been a major tragedy in your life. I don't know if you want to say anything about that or not.
Yeah, I mean, it's definitely been both, right? I mean, I could probably draw a spreadsheet and put the pros and cons, you know. Obviously, I was very fortunate to meet with a very supportive community of people. As I said, I you know, met my wife through that community, and those would definitely go in the pro column. But obviously the downsides, you know, having your life basically put on hold at a very sort of critical point. You know, I was in my early 30s, starting my career. I was on this rising trajectory, and everything just came crashing. So that's would definitely go on the negative side. But I think, you know, I mean, it's. From me, I guess maybe I have a positive bias in life in general. And so I like to see what I can get out of that and turn it into a positive, even knowing that there was a lot of negatives associated with it.
Okay, thanks.
That's my own bias.
I have a question too.
Yes.
Many cancer patients unfortunately get diagnosed a bit late, you know, in the journey, and you got diagnosed early-ish, not that early, but early-ish.
Yeah.
So what were your symptoms that brought you to seek medical attention?
Yeah, so I mean, it varies by cancer. In my case, it was fatigue, and I could feel that there was something wrong, like a tumor kind of thing. But you know, depending on the type of cancer, there may not be symptoms. So I know, for example, women with breast cancer, you know, so they encourage regular screening so you can identify early symptoms. But other types of cancer, like you know, ovarian cancer, for example, there are no external signs. And by the time you get diagnosed, you could already be in a stage 3, 4, you know, and so it's very, very difficult. So I feel like I was very fortunate that the cancer was caught early enough, and that type of cancer nowadays has a 90% survival, 5-year survival rate. They always calculate they don't care about what happens after 5 years, but the 5-year survival rate is 90%. And the treatment for that was developed in the 70s, which means that if I had been diagnosed with that cancer before the 70s, my survival rate would have probably been under 20%. So it's a matter of luck and history and techniques.
Well, thank you so much, you know, for sharing your experience with us and showing us how this has shaped your research program as well, you know, and it's such an honor to have you here sharing this, but also as a U Ottawa community member. So thank you so much for your time. Thank you all also for assisting and participating and asking questions. And thank you also to our online audience. We have from the Life Research Institute just a little thank you for you.
Thank you.
Thank you so much. Huh?
It's an adventure.
Dans des clés USB dans les salles de cours.